Okay. Well, thank you all for being here today, and thank you for the organizers for inviting me to be part of this. I think it's a great way to meet folks in the department, especially when you've recently arrived. Like it says, the community project, I think it's a great way to meet you guys and develop that sense of community. So I am Krishnan Mahesh. I go by Mahesh. I am fluids faculty in this department. Specifically, I work in the area of computational fluid mechanics, and I'll tell you a little bit more about that in today's talk. If there is anything you see that you find interesting, want to know a little bit more about, this is the website that has more detail in terms of papers and, a little more detail about what I'll be talking about. In addition to research, this semester I'm teaching 423, which is a tech elective in computational fluid mechanics, and we hope to also offer something, a follow-up course to that in the near future. So I've titled my talk From Mumbai to Michigan, and what I thought I'd do is in the first part of this talk, tell you a little bit more about myself from by way of personal detail. I come here prior to coming here, I was faculty at the University of Minnesota. So then I thought I'd give you a few vignettes of what life was there like and the kind of work we did. And then we'll talk about NAMI research that I intend to conduct as faculty in this department. And if at any point there are questions, please feel free to stop me. So I was born and brought up in Mumbai, which is in India. And if you look at this map here, that's Ann Arbor, okay? And that's Mumbai. And it's about 8,000 miles from here, 11 and a half hours different by way of time. And so if you flew from Detroit, it would take you, depending on how you flew, something like 16 to 20 hours roughly to get there. Now, Mumbai is an island, okay? And what this picture shows you is what's called Marine Drive. It's a section of the coast, okay? It's called Marine Drive or Queen's Necklace. It's a very pretty sort of part of downtown Mumbai, very popular during the evenings and on the weekends and so on for folks to go and spend time there. Now, not everyone lives in Marine Drive. I grew up, a lot of people live in suburbs of that area, and I grew up in one such suburb called Ghatkopar. And this apartment building is kind of representative of the type of apartment building that I grew up in, and most people in that part grew up in. You notice the nice high rises are on the coast. Now things are changing in that, as development, things are growing inward. And so apartment buildings like the smaller ones are now, being torn down and high rises appearing in their place. Of the many, it's a great place to be. I think it's a great place to visit, even if you weren't born there. And if any of you do, one reason to visit, I think, is the street food in Bombay. Yeah, so I just wanted to show you a picture of that. This is an example of a street. It's a location called Cow Gully, which literally translates as Eat Street. Yeah, and so it's like Eat Streets here when we have them, that there's really a bunch of stalls on the street, and it's very common in the evenings or at nights. You just go there and hang out and eat, basically. And the food's quite excellent. And now you have these things in different parts of the city. This one is a picture from the suburb that I grew up in. From kindergarten through high school, I attended OLPS High School, Our Lady of Perpetual Succor High School. And these are some pictures from there. Okay. So this is a picture of our school building. Yeah. So these corridors here, there were 3 stories. These corridors here are where the classrooms were. This picture is a little after I graduated. Now things have changed a little bit in that this is covered. This area here, this quadrangle is where we'd line up for assembly. You probably don't see it, but you see this hoop is attached to a balcony. And that's where the principal or the teacher would come, and there's a weight lineup, and there's a hoop here, and then a big stage behind. And it basically still looks the same, except the top is now covered to protect from the weather. This is the back of the school building, and there's just this big field, where typically you'd see soccer and cricket for like the most popular sort of things to do here. And I found this picture. It's a little after I graduated. I mean, faces are probably not clear to you, but it's a picture of the teachers there, many of whom, taught me. So this is Mr. F.E. Acharya, Mrs. Lawrence, Mr. Estrado, Mr. Dubey, and so on. And thanks to things like Facebook and WhatsApp, we still know what they're doing, what they're, it's people are still in contact. And so this was a really nice period in that we grew up with friends from kindergarten through high school. A lot of us, a lot of whom are still in contact and, in touch with what each other is doing. I went to undergrad at the Indian Institute of Technology, also in Mumbai. So it was it's about 10 miles from where from my parents' home, but I stayed in a dorm on campus. And this is a picture of our dorm. It still looks, it looked like this when I went also. And there's a picture on the outside, and you see it says Hostel 6. So the dorms are called hostels and Hostel 6. And so every hostel had rooms. In addition, it also had a dining hall. We called it a mess. And the students, we kind of organized, and you had a mess secretary, and then you decide the menu, what to buy, but you had permanent staff who did the cooking and so on and so forth. And so dorm life was a really fantastic part of, I think, undergrad years, where you stayed in the same dorm from freshman through senior year. And so you stayed with the same group of people who came from all parts of India. And the result was, you made very long-lasting friendships. And so this is a bunch of us who attended our 25th year reunion, right? So some of us have white hair, some of us don't have much hair, but it was all still a very good time. And again, those years were really great in terms of making long-lasting friendships. And so life here was, you'd get up and then go down to breakfast, all of you eat together, walk to your class, come back for lunch, do lunch, go back, and then come back in the evening, and then typically spend time on sort of intramural sports or things in the dorm itself. Typically volleyball and cricket and soccer were most common. We had like 2 or 3 fields there. And then in the evening after dinner was when people would start working their homeworks and things like that. And that was a really nice part of life, where you'd kind of work in each other's rooms or in a common area. And not everyone would attend every class. So that some folks would, so you take, if you attended, you take your notes, leave it outside your door, and then you go to bed, somebody else comes, takes that, studies, and then, you kind of, it was, so life in the IIT, and the hostels were really quite enjoyable, I'd say. I got my bachelor's in mechanical engineering. Actually, there you're required to do a final project. Everyone's got to do a research project. And mine was actually experimental. It was called forced convective heat transfer in a shrouded rectangular fin array. So you basically had this fin array, right? Fins, you use fins to increase heat transfer. And the idea that my advisor there had was, if you break these fins up to disrupt the boundary layer, will heat transfer go up? All right, let's go. Now, when you do a heat transfer experiment, you've got to insulate it. Okay. And back then, what I was told, we used for insulation was fiberglass, okay, or a glass wool. And you had to wrap it around this whole duct and channel, right? You had to wrap it around. And anytime you needed to access the inside, you had to take it off and then wrap it around. And I did as I was told. Oh, and so the end result was I got fiberglass all over myself for a year. And if you've ever handled it, okay, and I do not recommend you do it, yeah, you take it and then you try to get it off and you do this, it makes it worse because it drives it into your skin, yeah? And so I looked this up in making my slides. I looked this up on Wikipedia, and this is what it says about fiberglass. Fiberglass will irritate the eyes, the skin, and the respiratory system. Potential symptoms include irritation of eyes, skin, nose, throat, dyspnea, sore throat, hoarseness, and cough. I can relate to that, not all of it, but certainly a lot of it. So the end result was, so at the end of that, this was a year's experience. I said, maybe, I should just do computational fluid mechanics. That's a much healthier choice. What's the worst that could happen? I might drop something on my toes, and that's all right. You heal from that and you move along. So it wasn't a deep passion for computational fluid mechanics that made me go down this path. I just felt it was just a sense of self-survival. Okay, that took me down this path. So following IIT, I went to Stanford for grad school, where again, both my degrees, my master's and PhD, were in mechanical engineering. And in thinking about those years, there were a few things that were some of the more memorable things, were that I got to Stanford in September 10th or so, the first week of September. The Loma Prieta earthquake, you probably not heard of it, but it was like, you have the US. So it was like, it was 6 on the Richter scale, and that hit a month later. All right. So I got to experience my first earthquake ever, like a month after I came to the US, right? And I still remember I was sitting in my room kind of doing something, and then the ground starts to shake, and first you don't believe it. You don't know what's happening. Then you kind of hear a sound and it gets more intense. And then dresser drawers started opening, right? And things start sliding off your desk. And somebody had told me when I got there that when an earthquake hits, you stand underneath a doorway. So I jumped and stood under a doorway, but the dresser came and hit me. So then I went into the closet. That's all I could think of. I said, if something falls on me, let it be clothes. And then when the thing stopped, you just run out. And then for another 2-3 days, you'd have aftershocks. And it's interesting how you get used to it, because then an aftershock hits and that too is strong, but you're like, all right, just a tremor, just sleep. Very quick, very quick. So that was my first earthquake ever. A couple of other sort of things, the memories that stay with me forever, had to do with car 1 and car 2, my 2 cars. So I didn't drive in India. So I came to US, and when I came, I brought, I think, $200 with me. I couldn't afford to buy a car. After like a year, I saved some money and bought my first car. And I bought it from this graduate student who was leaving, to go take up a job somewhere. And he sold me his 1990 Ford Escort for $1,000. I was like, all right, I'll buy it. And then a friend taught me how to drive, which was another experience. So I learned how to drive. That's not my car. It's that model. It was kind of looked a lot like that. The color was a little different, cream, but basically the same model. So that Ford Escort, I went with Juan. He took a good buddy of mine. We went to my driver's test, right? And I was nervous enough that we got there and I locked myself out of my car.
Oh, no.
We get there, I get out, and I've locked myself out, and we're late, right? What do? So we call a locksmith. That guy comes, and it takes him like 30 seconds, less than 30 seconds. Yeah. He just opens it, right?
There's a bar that goes in and slides.
He just opened it. And then I had to pay, of course you pay. It was like some $40, $50, which is a lot of money at that time. And so I went in for my test. I'm thinking about the $50 and what a fool I was. And I failed the test horribly. I get out, I jump a red light. She asks me to go right. I turn right from the leftmost lane. Then I drive 40 in a 30. I failed that test. The only thing I got right was a triple point turn. And then I argued with her, trying to convince the examiner to make me pass, but no, didn't. So it was like 3-4 days later. In those days, you could take the test the same week. You didn't have to wait. So I failed it on Monday and passed it on Friday or something like that. So anyways, passed the test. And that car, after like a year or something, it wouldn't start. It just wouldn't. It would just not start. So I took it in to this mechanic, right? And he goes, well, there's your this thing head is cracked. There's a leak, right? So and so that thing is water is leaking at you. So what do? Well, you got to fix it, right? How much will it cost? It's like $1,500. I realized I paid $1,000 for this car, and I don't have $1,500. So I told him, just keep the car. And I got my stuff out of the car and just walked away. And I called my buddy Juan, he picked me up. Again, no car. So you need another car. So this time, another, we were office mates together, Steve's from Peoria. So Steve was like, I'll help you find a car, right? So the two of us go car hunting, need another car. And I end up buying this. This was a 1985 Oldsmobile Calais, okay. Looked great. And it was the first 6-cylinder car I'd ever driven. And that kind of sold me. I test drove it. Boom, it was like a rocket to me. Never driven something. I was like, Steve, got to buy this car. You sure? Yeah, got to buy this car. Okay, we bought it. And this, I think I paid $2,500 for it, a little more money back then. Bought it, and I brought it home. Next morning, the car won't start. Car won't start. And this guy, the guy who sold me, he said he had gone through a divorce. It was his wife's car, and he sold it to me. And so I called him and said, hey, the car doesn't start. Has this ever happened to you? He says, no. I was like, oh, okay. And I put the phone down. That is how stupid I was in those days. But anyways, this is a great car. The inside is like, had these blue seats and 600. It's just great when it ran. But then it had this quirk where you drive it down the freeway, then you take the exit, and if you stop the car, it won't start again. It'll just die. It was the weirdest thing. It's great, right? It's smooth as silk on the freeway, or if you're driving, a little distance. But you pull off, or if you were to stop at a light, this car would die, and it would not start again. It needed like 10 minutes or so, and then it would start. What do? I can't fix, and the problem with that is, you take it in. When I took it in, the thing is running, so there's nothing to fix, right? It was really stressful. So then I got to saying, okay, I can't fix this thing. And so what I would do is to not take the freeway. I had to drive, I just take El Camino Real. That's like Washington, a little bigger. And then I had to drive, typically I had friends and family, about 10, 15 miles. I would only drive in the right lane.
There's a light every 100 yards on you.
What's that?
There's a light every 100 yards on you.
Exactly.
Yeah.
And so, and then there's like stores on the right-hand side. So I would only drive this car in the right lane. If I had to stop, I'd immediately turn right into, take a right turn into like into a parking lot. And then I'd drive out from the other side. So I would drive like 10, 12 miles without stopping this car. That was the goal. That was stressful. Then I knew this, he's a very nice guy, Don, he was a mechanic there. And he said, this is really interesting. So he took it on personally. So he took my car, and then he had a buddy with the same car, and then they swapped whatever they could, right? And he said, I'm going to figure out what's going on. And he figured out it was a sensor, a little oxygen, some kind of sensor had gone wrong. And he fixed it for me. And he was so nice, didn't charge me much for it either. And after that, this car ran. Then it had some other problems, at which point I kind of just gave it up. So that was car 2. Yeah. The other experience I think that I got, that was really, I think I gained a lot from it, was one summer I didn't have the money to go home. So a friend said, you want to do karate, right? Shotokan karate. He was part of a club. I was like, yeah, sure. Why not? So went in, and I was not expecting to get anything, but I liked it, ended up liking it. The end result was I did that. It was part of a big national, international organization. They even had also, I think, a thing in Michigan here. But I did that for about 8, 10 years. And it was really great in terms of meeting people from all over the world and traveling over the US to do stuff. And this is not me, but it might as well have been. And on the academic side, my PhD was called Direct Numerical Simulation and Analysis of Shock Turbulence Interaction. That's kind of what I worked on for my PhD. So following that, my postdoc years were spent at the Center for Turbulence Research at Stanford, where I wanted to do something different. So I ended up working on vortex breakdown modeling, simulating plasma discharges, and starting work on basically simulating flows in very complex geometries. And back then decided to do this, a real gas turbine engine combustor, which we ended up achieving after I moved to Minnesota. And probably a biggest achievement was, getting married during that period. My wife, Pratibha. So this is a more recent picture. I cropped my kids out of it. My daughter wasn't very happy last night, my 10-year-old. But all our photos are in boxes in Minnesota still. But those were kind of the postdoc years prior to moving to Minnesota, where I obtained a faculty position. And so the move from Stanford to Minneapolis was, we found it exciting. So we didn't have kids then. So we just shipped all our stuff, including our cars, rented a car, and just packed it with, clothes. We had, I think, a sack of rice and some bread, breads and a rice cooker, instant food, beer. And we decided we just take 7 days, right? And just drive. It's about 2,000 miles. You can, if you drive continuously, you can do it a lot faster. We said we just take 7 days to drive. And back then you didn't have GPS. Yeah. What you had was AAA, and there was something called AAA triptych that some of you may know. So you had to go to the AAA office, tell them, hey, I want to drive from A to B. And this nice person would tell you, oh, this is your route, this is how you sketch it. At the very least, you'd get a book with the map, right? So we just grabbed that. And we said, we'll just stop wherever we feel like. We had food. That was the whole point of taking the food. And we were on a budget. We couldn't just, eat whatever. So we just stopped wherever we felt like. And this is what we felt like as I was collecting my thoughts. We first stopped at Auburn, which is in California, at the foothills. It was snowing when we got there. And so we said, we'll just spend the night in Auburn. The next stop was in Winnemucca, Nevada, which is on I-80 after Reno. I mean, it's before Elko and Battle Creek. Next night was in Salt Lake City, then in Utah, then Idaho Falls, then Cody, Wyoming. And that was really an experience because this was in October. And so it's like we had Yellowstone all to ourselves kind of thing. It was really an experience. Summer is more convenient, but if you can make it and weather cooperates, I'd strongly, strongly recommend that. It's a very unique kind of, it's like you don't know where to look. That's how pretty that place is, and you have it all to yourself. From Cody, then the next evening was in Wall, South Dakota. Maybe you've heard of Wall Drugs. And then we had about 12, 13 hours. That was the last. We had to pick our keys up. So we just drove and made it. We had a place in Minnetonka that we rented. We reached Minnesota on Halloween 2000. And it was memorable that I got a speeding ticket as soon as I crossed the state border. We literally were like, hey, this is Minnesota. And he wasn't very understanding, gave me that ticket anyways. And it was in Minnesota that I experienced my first snowfall ever, just a week after getting there. Notice, I still remember the experience. Prior to that, the only time I felt that cold was when you open a refrigerator and stood in front of it, looking for stuff, and you feel this cold, right? I was like, God, that's what this feels like. This is quite, but then you get used to it very quickly. I guess blood thickens or whatever. But in a week, 10 days, you just get used to it. And then you start looking forward to the winters after that. And so it was in Minnesota that our kids were born. Both of them were born there. They're Minnesotan. And academically, we until now have 25 PhD students graduate from the group there. 5 more will graduate in the next year and a half. At Michigan right now, we have 2 PhD students plus a postdoc who will join soon. And I am looking to build the group up fairly quickly. We've had around a dozen, 10 to 12 people there at Minnesota Steady State. So we want to build the Michigan group up to that. And so please do come by and talk to me if interested. And to give you a sense of what the Minnesota, things were like at Minnesota, this is a picture of our lab here. Basically, whoever was there the day this picture was taken was who's in the picture. And, we had these workspaces, and it was very friendly. The idea was people talk to each other, help each other. and so on. That was the lab there. This is a picture from a reunion in 2018, where everybody from the very first students to the students who were there came with family and kids and all that. We had about 30 to 40 people came, and we spent a day together. This picture was taken there. That's Goldie Gopher, Minnesota. And we had this tradition that whenever, for special occasions, we'd go to Stub and Herbs, which is a local watering hole. This was after Praveen's PhD. Praveen's PhD celebration. And this was just before I left Minnesota to come to Michigan. A whole bunch of us went to Stub and Herbs again. And typically as a group, we'd go to meetings, the APS, American Physical Society, DFD meetings are pretty common. And so we'd go as a group and usually do something together one of the evenings when we were there. So next, I thought I'd give you a sense of some of the research that we did there, and then talk about research focus here. So turbulent jets and cross flow are something that we've spent some time working on. And so this is what the problem really is. Okay, how does crosswind disperse volcanic plumes like this one here, right? There's ash and stuff coming out, and crosswinds carry it, and aircraft engines can get snuffed out, or weather can change. If this happens in Europe, it goes across continents, right? And you shut down airplanes and all that. This is an oil fire. So how does that smoke from that go? In gas turbine engines, you have dilution jets that cool combustion products and reduce NOx. That's how you get more uniform exit temperatures prior to the turbine, as well as lower levels of NOx. And so we were interested in problems like these, and which we studied using numerical, high fidelity numerical simulation. This is from a simulation of that Suman did, and we call it high fidelity in the sense that, we expect the results agree with experiment sort of like this. Okay, we have the solid lines here, symbols. So we performed simulations like these and asked questions like, how do things mix? How does the trajectory evolve? And if I change the parameters of the problem, how do these things change? How do we control these jets? So on and so forth. Okay, so this is an example of one problem that we worked on there. Another one that Mike Mattson worked on for his PhD was, can bubbles over ship hulls reduce drag? So this is something that was experimentally looked at here in Professor Cesio's group. We developed a simulation capability for this. So this is a boundary layer, and bubbles are being injected at this location. And this is sort of a view from the simulation of a plane parallel to the wall. And the reason you expect bubbles to reduce drag is that they have gas in them. And so the kinematic viscosity is lower, right? And so it's like you're covering the hull with something with a lower kinematic viscosity. And so you expect the drag to be less. The upshot of it is the simulations, as well as the experiments, showed that, yes, bubbles can reduce drag, but not over long distances, because the turbulence wants to migrate the bubbles away from the wall. That's called turbophoresis. Yeah. And so this is an example of another problem in another flow regime that we worked on. Another thing I thought I'd share with you was a problem having to do with the aerodynamics of cacti. Yeah. So this picture here shows you what's called the saguaro cactus. Okay, they're found in Arizona, for example. Yeah, and there are pictures here to give you a sense of scale. So saguaro cacti, they're pretty tall, 26 to 50 feet, but their roots are only a foot long. And they live long enough, right, in the desert. They experience very high winds. Now, if you just took a tree or you took a smooth cylinder and you stuck it in winds of that strength, they should not be able to, they can't last, right? You wouldn't build something that's 50 feet tall and put it a foot under the ground. But these do, how? So we looked at the possibility that the geometry of the cactus could be modifying the flow and therefore the loads. And so what we did was to use, think of flow on a smooth cylinder. That's your baseline. Now think of flow around a cylinder that's serrated with grooves that are representative of cacti grooves. This is that cross section. And what we found is that this geometry did affect the flow and thereby affect the loads that it would experience, suppressing it. And this, we use simulation, this, that, but this is kind of the bottom line as a schematic. If this is a cross section of the cactus, when you have flow over it, if you have a groove like this, there's going to be recirculation within this groove, right? And so what this high speed flow sees is not the no slip condition here. Instead, it sees this low velocity fluid. And so the shear stress here is lower. And that also, it makes the flow more quiescent. And so the fluctuating loads are also less. Yeah. Another problem of interest was, how does surface roughness cause supersonic laminar flow to go turbulent? And the reason this problem was important is as follows. So this here is a picture from this paper, which basically shows you gap fillers on the shuttle. Okay, so basically it reels up when something like when something re-enters. Okay, if you have protuberances, okay, or you have large roughness, or you have breaks in the heat tiles or gaps, then those things can cause laminar flow to go turbulent. All right, that's transition. Now, when the flow goes turbulent, your heat transfer and drag go up. And heat transfer is what constrains the re-entry problem, because it's really hot. And if you break through the tile, then you're burning, right? That's a failure. And so the idea is to be able to predict how things like that can cause transition. And the reason the study was important was that engineering models have difficulty in predicting transition. All right. And so what we did was to look at a representative problem like that. This is one of them, where you have a single protuberance in a supersonic flow. It's all laminar here, okay, but downstream you see it's completely turbulent. And the simulations were able to explain or provide a mechanistic reason for why that would happen and why models might have difficulty in predicting things like that. How do supersonic jets interact with crossflow was another problem I thought I'd share with you. So what you have here is basically a jet that's coming at Mach 1. It's interacting with the crossflow at Mach 1.6. These simulations were done under the same conditions as experiment. And you're looking at the flow in two planes, vertical and horizontal. All right. The reason you care about a problem like this has to do with scramjet injectors, scramjet engines, okay, where fuel is injected, mixes with free stream air, and that's how burning occurs, right? Combustion occurs. Another application of these things are in what are called thrust vectoring, where in something like this, you send jets out from the side, right? And the resulting thrust allows you to roll and attitude control. And this gives you a sense. So we developed the capability, the code, and so on to do it, ran it, and things agreed with the experiment. But then we were able to look at the complexity of the flow and explain how the two streams actually mixed in the near field and what the relevance of that was. So in the remainder of this talk, so those were some examples of things that students worked on, that our group worked on at Minnesota. In the remainder of this talk, I thought I'd speak to NAMI research, okay, whose overarching vision is as follows. All right. When we think of basically the flows, namely naval or marine relevant flows, are quite complex in terms of geometry. They're complex in terms of the physics that they have. Okay, and what we'd like to do is to basically develop methods to predict those things reliably. So by way of to address sort of practical engineering problems. Now, by way of example, this here is a submarine that's inside a water tunnel. Now, imagine something like this going through the ocean, right? The propeller is spinning, control surfaces are moving, right? This thing may be pitching up and down, yawing left and right, but it's going as it goes through the ocean. Now, the flow over this thing, right? You have a long hull, so the flow over that hull is turbulent. Yeah, there's a very thin boundary layer that's entirely turbulent that comes over the stern. That stern flow interacts with the appendages. And it's a flow that's the highly non-uniform flow after that interaction that goes into the propulsion, right? And that produces thrust, yeah? And then there is a wake here that you care about. Now, what are some of the things that you care about? You care about the loads on this, not just the resistance. If you're at angle of attack or yaw, you have unsteady loads that you need to be able to predict. If your appendages are moving, do you have the control authority? that you need, right? The propulsor itself, okay, one situation is it's producing steady thrust. How is that affected when all that non-uniform stuff comes in? If you're in an off-design condition, you need to stop in a hurry, right? You're going to spin it backwards. Flow is massively separated. When that happens, the loads can cause the blades to break and get damaged, okay? Your control surfaces here can lose control authority. How can you predict that? And what do you do about it, right? Water cavitates when it sees low pressure. Yeah, that happens behind propeller blades. It can happen when you maneuver. And you care about cavitation. When it's mild, I'll show you a video later. When it's mild, when cavitation incepts, it produces intense sound. Okay. When the cavitation is large, it can cause metallic surfaces to erode. How do you predict and account for that? Maneuvering, I already said this, right? How do we can we predict detailed maneuvers? And can detailed simulations allow us to develop simpler control laws? And then sound. Yeah, that's very important from a detectability standpoint. Water is dense. When it goes over surfaces, causes it to vibrate. Okay, and when that happens, you have noise that forms. Can you predict it? Can you? And why bother doing research in any of this? Well, traditionally, for complex flows, it's only the time averaged flow that's computed. But when the physics is fundamentally unsteady, okay, these methods are inadequate. And the question is, can three-dimensional unsteady methods be developed that do this? And that's what we do. And so can we develop these methods? Can we reliably predict these things? And if we can, so what? What do we learn from those validated simulations? So that sort of is the overall vision of what we do. Now, why is this worth doing? What are the challenges? Okay, in very sort of bulk terms, the main problem with these flows is that you have a very wide range of length and time scales, meaning you have very small flow motions over long distances. You have things that occur very fast, along with things that occur very slowly. And what that means when you're trying to compute things like this is you need you need small mesh elements over big distances. You need small time steps integrated for long times. And that's cost. That's computational cost. Okay. And so the pacing items at a research level, what are the students doing in our group? They're developing numerical methods, turbulence models, physical models, like when you have cavitating flow. They're performing simulations on the largest computers in the country. These are things we use tens to thousands of processors to run our things, and large-scale data analysis, terabytes and terabytes of data. Okay, and so when students graduate, they are experts in scientific computing, fluid mechanics, as well as HPC. Okay, so by way of background, how did all this start? In the early 2000s, we performed the first time LES of flow in a real PW6000. This is a combustor. This is a real Pratt & Whitney combustor. They just gave us CAD files. We had never done anything like this back then. We were doing simple structured geometry. So even working with an IGES file was a thing back then, and computing flow like this. And the key development here was numerical methods that are robust and accurate without numerical dissipation. 4 years was spent just dumping core. The code would just crash for 4 years until the numerics fell in place. And it just, it was like the clouds parted and birds started singing. And in like 3 months, everything kind of just ran. We call our code MP Googles. It's entirely in-house, okay? And these codes are not a black box. Students actually work with them, okay, with source code. And we are involved in a number of collaborative projects involving the Navy, as well as other universities around the country and abroad, and students interact with those groups. A recent capability that we've developed and are now is shown on this slide. It's called an unstructured overset methodology for moving bodies. And this picture kind of gives you a sense of what it is. So the red contours here, this is just flow in a channel. Do you see little specks here in this picture? Now, if you zoom in over a little volume, okay, this is what you get. So each speck is a particle. And you see this thing here? This is a mesh around each particle. So what's going on here is you're solving the fluid equations on about 100,000 meshes that are moving on a background mesh, distributed amongst about of the order of, in this case, around 10,000 processors. Okay, that's what cement band structure oversight. Now here you're doing particles. And to do this, these are two key challenges, numerics and parallel scaling that we address to do this. Here you're doing particles, but now what we want to do is to take the same capability and apply it to a maneuvering body, all those problems that I talked about earlier. Okay. And these are some examples of where we are as we are kind of developing this capability. So this is flow around a ducted propulsor in what's called crashback. So you're going forward while spinning in reverse. This is a duct, this is a rotor, and you probably see the stator in the background here, right? And so when this happens, the flow is massively separated. And I'll just to draw your attention to this big thing out here. You see this big ring here? It's actually a ring vortex that sits outside the duct. This is what causes all the unsteady side forces that you care about, impinges on the appendages and so on and so forth. And then you see this little gap here. There is highly separated flow in that region that the simulations pick up. And that flow in that gap is the reason that the side forces in crashback in the presence of a duct are extremely high. And the simulations are able to predict that. And this is a picture, but I just wanted, the details are not important. But basically, we are comparing to experiment. One of these curves is a simulation, the other is experiment. Okay, the agreement is fairly reasonable. And so this is when we consider the simulations validated. Other problems, other propeller problems that we've looked at, I just summarized a couple. We've looked, this is flow through an open propeller where we were interested in the mechanism of wake instability. Again, the results agree with experiment, and because they agreed, we were able to use them to explain that. We've looked at the effect when you attach a propeller to a hull, to a stern, then the proximity to the stern affects crashback loads. We've explained that. And we've used simulation results to predict sound that propellers radiate, that this paper by Jacob describes. And presently we have work going on cavitation and ducted propulsors, tip vortex cavitation and ducted propulsors. This is an example of flow simulated over the entire, we said we care about the entire hull. This is flow over an appended hull. That's a sail. There are appendages here. And this is at what you'd consider a low Reynolds number compared to what happens to full scale. Okay, it's 1.1 million, but gives you a sense of the detail that the simulations have. You see these little things that look like flow structures? This is what causes resistance. So when you do resistance studies, right, you tow something and you calculate the resistance, you get one number, right, for the net drag. In reality, what is producing that drag is that highly turbulent boundary layer near the surface. And within that turbulent boundary layer, you have these very small motions. Their integrated effect is that one number, that's resistance. Okay, so that's the detail that these sorts of simulations represent. And this just quantifies that for you. Pressure coefficient, skin friction. And right now there is work on it. What we care about is going from model toward full scale. As you increase the Reynolds number, it gets more challenging. So how do you address that challenge? Okay. Toward maneuvering, we've also done work that, again, we want to extend with the overset capability on attaching a propeller as shown on the top. And on the bottom, and this is quite interesting, we are now able, see, when you do experiments on something, you got to do it in a small facility. That's called model scale, right? Compared to what you do at full scale in the ocean. And when you do that, there's a big difference in Reynolds number. And so what model scale experiments have to do is to trip the flow to make it go turbulent so that it's more representative of what happens at high Reynolds numbers. Okay. Now, while people know that trips matter, how they affect the flow isn't quite clear. And now we are at a point where we can actually resolve those little trips that the experiments use in our simulations. Okay, and we've started to do that over the last 2-3 years, and this promises to be quite interesting in terms of establishing the connection from model and full scale. This is an example of flow over of an external flow, or what's called a prolate spheroid. It's part of a big project that Professor Dowling is doing the experiments on. These experiments are going to be performed at the largest water tunnel in the world, the LCC, and we are doing simulations of that. And this gives you a sense of where we are. You see this thing here that looks like a ring? Well, it's actually not a ring. It's 238 cylindrical posts. Okay, and we are resolving the flow. The same thing that we used to resolve each other's particles, we're resolving these posts on. And what this shows you is how the flow turns. It's called cross flow, comes here to the leeward side, and then separates to make these big vortices. These big vortices are what cause big unsteady forces. So when something maneuvers, stuff like this is forming, okay, and affecting the loads. So that's why you care about this. And we are not there yet, okay? We are not, this is very much something that we are actively developing and hope to. So cavitation refers to how liquid becomes vapor in regions of low pressure. Okay, that's cavitation. Why do you care about it? I wanted to show you a couple of examples. Basically, cavitation increases noise when it just starts to incept. And here is a movie. You hear that? That's real noise as picked up by microphones in that experiment. Okay, it's the flow that's producing that noise. It's cavitation that's producing that noise. Okay, and this is from a little hydrofoil in a tunnel. When this happens under the ocean, if this happens behind your prop, everyone knows you're there. Okay, so this is why we care about cavitation from a detectability standpoint. If the cavitation is large, it can cause metallic surfaces to erode. That's what you see on that rudder there. And you've probably seen this in little boats also. You can see pitting on propellers, and it's a result of cavitation. So we would like to, can you simulate it? Can you predict it? All right. And here is an example of where we are in this process. We first looked at cavitation in that erosion regime. You have a big cavity which forms and collapses. Can we compute it? Prior to this, people quantitatively did not predict cavitation. But Steve Sessio here at Michigan performed experiments, and Steve and Harish performed experiments on what's now called the Michigan wedge, all right? So this is a wedge, flows from top to bottom, flow cavitates, okay? This white thing, this is a simulation result. White thing is basically vapor forming on this wedge. It rolls up into this cloud. Cloud comes into high pressure, collapses. And you have strong pressure waves traveling up and down in this flow. Yeah. Now, when that happens, the experiments showed, and the simulations are able to reproduce it. Basically, there is a big shock wave that travels at supersonic speeds. This is water, mind you, right? You don't get even compressible flow in water. Isn't density supposed to be constant? It is until it cavitates. Okay, now it's bubbly water. And so sound speed's very low. And so you have shock waves traveling at supersonic speeds. And this is a quantitative comparison to the Michigan wedge experiments. All right. And so the whole point here was developing this capability to where we could have some confidence in predicting these large cavitating flows. And so this work is going on in the direction of further improving the modeling as well as applying it to more complex configurations. So for example, there is a difference between gas and vapor. Water vapor is not the same as gas, right? Water vapor is related to liquid by thermodynamics. One converts to another. Gas is gas, doesn't dissolve in water, right? And so it matters whether you have gas bubbles or vapor bubbles. How do you account for that? How do you predict cavitation inception? You saw that we can do a reasonable job on large cavitation. It just starts to form, okay, and it's very noisy. How do you predict that? This, I won't get into the details. We're starting to do that in the flow where these blue regions are where cavitation incepts. And we can show that it's little vortices that are stretched by the turbulence. And that's consistent with experiment. Can we develop a multi-scale cavitation model? Schematically, if I have a large vapor cavity along with very small bubbles, I can just put a mesh and resolve the small bubble and the large guy, right? You got to model this while resolving that. How do you do that in a consistent way? The small can become large, large can become small. There's work going on in there. Cavitation starts from small nuclei, okay, very small nuclei in the ocean, water tunnels, so on. And right now, it's just an empirical thing. We just assume something. Can we predict it from first principles? So we've developed an approach and are developing an approach to do that. So these are the sorts of things from a physics modeling perspective. We have work going on in fluid structure interaction and sound. So the practical relevance here is that if you have that crashback problem, the transient loads are such that they can cause metallic composite blades to break. The strain rates can be very large. How do you predict it? A normal propeller or a surface of a hull where you have panels, right, to absorb sound, those are compliant. And water is very dense. If you ever stuck your hand right in a boat or something, just stick your hand in the water, you know it. So water being this dense causes those panels to vibrate. When that happens, the vibration contributes to noise. Yeah. So can you account for that? And so we're interested in cavitation erosion is another example of fluid structure interaction. So this is one example of where we are in this process. And I just in words told you things that we care about going forward. What you have is a turbulent flow that we computed using MP Googles. On the bottom, you have imagine a plate. Okay, there's a plate. This plate responds to the flow, and we calculate using, we developed an in-house FEM capability. We calculate the deflection, unsteady, all right? And when that happens, it radiates sound, and we can compute the far field sound using acoustic analogy. And so we want to use things like this to ask questions like, I care about something's going on here, right? And I care about, say, sound here. What part of the flow contributes to the sound here as a function of frequency? How do you answer that question if you have volumetric data, this full detailed data? And we've developed, for example, in this paper, methods like that. And the idea is to take this capability and now use it to look at things like, well, what if I had Kirigami surfaces? Can I use them for surfaces that were more complicated than just, flat surfaces that are compliant? How do I do erosion, for example, so on and so forth. So these are all examples of things that we care about going forward. Biofouling is something we have an interest in. And what biofouling, you put something in the water for a while, it's covered with crud, right? So it's, and so the real surface is no longer nice and smooth, yeah? There's stuff on it, and that affects the flow, it affects the resistance. So can we understand it from can we study that? So in this top panel, this thing here is a tile that was given to us by experimentalists at the Naval Academy. They scanned it and gave it to us, line scans. And we were able to basically convert that into a geometry over which we computed the flow, right? And that's what's really shown here. These little things here, you see those little bump-like things, they are the asperities in that rough surface poking out through the plane where we plotted data. So we're actually capturing flow within these cavities and things like that. And then using it to basically say, hey, this is why wall pressure fluctuations are higher, this is why resistance is higher, so on and so forth. That's what that was good for. And in addition to simulations, we also do things like stability analyses and so on. Computationally, you can't do them analytically for very complex geometries to actually answer how these complex flows transition, how trips work, and so on and so forth. Okay. And this is the future as I see it in terms of where we would go as a group, we would go forward, where the field would go forward. GPU-based acceleration methods, right? You can get an order of magnitude to 30 times speed up. And what that'll do is to basically allow LES for certain problems, allow desktop LES. And get us closer to full-scale simulations of the biggest machines we have. Multi-physics part of it, naval problems are extremely interesting and extremely rich in terms of the things to study. So surface roughness, transition, fluid structure interaction, cavitation, hydroacoustics are things I touched upon. Maneuvering is something we're just starting to do with this kind of capability. And that's going to open up a whole new set of things. And then free surface problems. We've done that in the context of super hydrophobic surfaces, but imagine things like big things being close to the surface or piercing the surface. How do you deal with that at our level of simulation? Numerics and turbulence model development, that will go on. Big data and model reduction, we are generating terabytes and terabytes of data. How do we make the most use of it, right? And so you can plot things like this, that's great, but can you also do more? Can you improve simpler models, so on? So this is of active interest right now. Data assimilation. You have an experiment going on and a simulation going on. Can they use each other's data, for example? Yeah. So we have a project right now going on along those lines. And there's a large number of multidisciplinary type things. Super hydrophobic problems are one example that we worked on, but things like soft and metamaterials, biofouling is actually pretty multidisciplinary, depending on the level you think about it, IC flows and so on and so forth. And so there's a lot of potential for collaborative type things in this domain. And so I thought I'd conclude with this, is that, I showed you examples of the finished product, right? So I thought I'd conclude with showing you what goes on under the hood. So this is like a typical day in our group, yeah? There's a whole bunch of equations. There's a person here who's working. He's working, she's working. There we go. All right. And then you start the whole thing starts. The next day starts all over again. Okay. So that's life in our group. Yeah. That's what happens on a daily basis. But then things do work, and that's our job. Yeah. It's figuring out what it takes to do these things right and do those things that are not possible today, but our days are, and that's what we do. So thank you very much for your time. Again, if you're interested, you know, this is, there are more details here. Also, I'm in 213. Feel free to stop by anytime. That's my email address. And like I said, I'm really looking to build our group here at Michigan up quickly. So please feel free to stop by and, you know, let's make stuff happen here. Thank you. The protocol, do we do questions or?
Questions?
Okay.
I got one.
Dave will go home first.
At the very bottom, I think one of the last slides you mentioned icy flows.
Yeah.
So what's in store there?
There's a need,
Oh,
right?
yeah.
In terms of studying that regime of flow. So if you just took the same kind of application that you have in, say, warmer waters, and imagine going there, then all your fundamentals, whether you're thinking of resistance, when you think of sound, think of cavitation, all of those things change. And so the scientific problems would be, you know, even what is an ice, starting from what is an icy flow? It could be anything from a Slurpee, right, to things where you have particles, I mean, where you have pieces of ice, and now start to ask turbulence, wave propagation, all those fundamental issues. So everything from chemistry to mechanics of ice to turbulence to flow, combining towards flow over a body, I think it's quite open depending on the level of fidelity that we look at it. And so the hope is that we can conceive of something that's more concrete, involves a lot of people, and take it as sort of take it forward. Yeah.
I have one question. Okay.
Yes.
Yeah, very nice talk. And I wonder the biophoning. I have one question regarding the biophoning. You know, this is so important problem, but it's very complicated.
Yes.
Biochemical or this physical process.
Yes.
How you address, how you solve such kind of problem?
Okay. So how you solve is what we have to figure out.
Your
now,
research method on how you address this.
So there are different levels. As a fluid mechanics person, the first order way to think of it is to say that what a biofouled surface does is to change the roughness. You think of it as changing the roughness of the surface. And so you grow something and then you take a picture of it, right? And then based on the geometry, like if you have tubes, they can be like tubes or they can be this distributed sort of algae, right, that grows on the surface. And you think of it as a roughness and you solve for flow over that, like in very much the case as you did over a rigid surface. Now, if you add more to it, you say, you know, how do these things grow? What are their mechanical properties? And if I look at it over a period of time, how do they change and deflect, allow for compliance? Then you toss those things in. So, and that becomes a fluid structures interaction problem from a mechanistic perspective. But then you can add other things to it. You have folks who study how these things grow. Right? They understand how they grow. And so that's expertise they bring to the table. We cannot, I mean, I don't, right? Then you think of the practical aspect of this problem. The way it works is you have some, you know, a diver goes down in murky waters and then takes a picture of a small section of the surface. Then it comes up, then they classify it into grades, right? This. And then from you have to correlate that to resistance. So what is that process? How do you go from that sort of visualization? And it depends on the level you think about it. If you want to go into it deeply, then folks who do autonomy and so on think at that level.
So this is very important to understand the biophoning. And the follow-up question is how to reduce the biophoning now.
Well, right now, again, how to reduce it is not something I can speak to, but right now the mechanism is one of chemical. You clean the surface.
Okay.
Like you accept, if you put stuff in the water, stuff's going to grow on it.
Okay.
You put a boat in the water, stuff's going to grow on it. And so it's more a maintenance kind of a thing that you have to deal with.
Can you talk just a little bit about your transition from undergraduate studies to graduate? Because it sounds like undergrad, you were with the same people living and studying, and then you come to the United States, to Stanford, new people, new places. That must have been very different.
Yeah, it was different. I didn't know anyone at Stanford when I came. And this was in the you didn't have the internet, right? So we thought that we were savvy we listened to Deep Purple and Pink Floyd and Jethro Tull, and we were like, yeah, the US. but then time came to coming here, and I didn't know all that much. And I was under the impression, for example, that everyone in the US wore suits all the time. So I went with my parents and we got a couple of suits, right? And so when I come to the US, I'm dressed in a suit. And this is summer, it's summer. And I still remember, I was the only person wearing a suit on that whole stupid plane. Everyone was in shorts, flying from Hamburg to here, and they show up. And also, I didn't have money with me, so I brought all my stuff in suitcases. Everything. I had like 2 weeks worth of food even, because I was planning, I didn't have a car, I didn't know anything, and I had planned, I'm going to cook my own food. Because I had $200 with me. And those little dogs in the airport, right? You come in and that dog wouldn't leave me alone. And I show up, and I had a cousin in Dallas, so I came to Dallas and got off, and that little dog was following me around. And the guy goes, "What do you have here?" "Nothing, just some food." No, you have some. Okay, fine, open it. And back then, the suitcases were not like they were. Even these little things, they sound silly, but there's two huge suitcases, and I think my parents were worried that it might break or something. And so my dad had these big nylon, ropes, and he had tied it like this, like that thing was not opening. And this agent wanted me to open the damn thing. And it took me like 15 minutes, finally open it. To make a long story short, they didn't find anything. Of course, I was the last person to get on the boat, out of that airport. So anyways, did that. And then came in and everything was new. I didn't know anyone, even things like grocery shopping. I mean, I was very surprised. I remember, like in Bombay, everything is crowded. You take a bus, it's full. You can't get that bus. I was really, my eyes are open still in Dallas, seeing these buses, beautiful buses, no one in them. I couldn't believe it. So it's things like this. And then in a small place in a city, if you ask someone for directions, where is this? They know, because they're used to walking, taking public transportation. Here, I was getting lost. And if I asked someone, they didn't know. And oftentimes it would be the building across on the other side of the street, because people drive everywhere. Also, I still remember watching like my cousin's friend dropping her daughter off at the school bus, the kid to be picked up. And she was driving 10 homes down. And I thought, wow, people are really wealthy to do this, it seemed. Now, I've turned into that person. It's not well, it's just lazy, right? You don't want to walk in the morning, you should do it. Then when I came to Stanford, it was, initially I was, there was some homesickness. I mean, I didn't know anyone and didn't have, because there you had a lot of friends, people, and then I'd go to class, I'd go to courses, and fine. First there was a sense of, ooh, wow, it's Stanford, what will I fit in? But then you realize it's not such a big deal, that gets out of the way very soon. Then it's more like, what am I doing here? What am I, yeah, I'm taking courses, I'm doing stuff, but do I really need to do this? Then when that earthquake hit, my parents are like, enough with grad school, just come back. So let's stick with it. Did that. But then what really helped is slowly things started. When I came from India, I'd asked for my roommates to be American. I'd made that request. And so I had two very nice roommates. Bob was from Peoria, Kevin was from San Diego, both very like all-American kind of guys, and I say that only because they then got me into things like, hey, you want to go to the weight room? So I'd go with them. Then I liked it. I took a class because I'd never stepped into a gym before in India, So fine, I took a class, and that gave me a social outlet. And then I met people, you know, in the department. We started doing, and certainly in those initial, although I had a stipend and all that, I couldn't spend. I mean, I had no money to really spend. So, but other friends were like that, like me. So we would hang out and, you know, just eat on campus or just a little outside. We'd walk to places and things like that, hang out in each other's apartments, do stuff. And about a year went by, and then slowly things started growing. In that after a year, you had a little more money, you could go out to eat, do stuff. And then you started doing things like, you know, the karate, this, that, you meet more people. So it was a slow process of sort of getting into that. And two things helped. I think after 2 years, I didn't mention it because I didn't want to mention their names. I moved off campus and rented a room in a house in the Los Altos Hills. So I had the mother-in-law room. So you had the main house, and then you had a corridor that went to the garage. There were 2 rooms. I was in one room. The next room had their 2 dogs. These are the nicest people, and it was a formative sort of thing for me, experience for me. Their children had grown up, and he was he had about 3 years of service left, then retired from Stanford. And they had moved there after the war, actually. Back then, Palo Alto was, people moved there to live in the woods. Okay, it was, and that was great. Living in sort of a house, seeing them, seeing their interaction, their prayer, this thing, and I'd make a little bit of extra money, walk their dogs, you know, go up the hills, this, that, and the other. But it really gave insight into family sort of life here. And initially, when you come to this country, I think you notice differences, but after a while, you notice similarities. And it's very easy to say, but when you experience it, it really changes your outlook. And so that was very formative. And I stayed there for 4 or 5 years until I got married. I think I stayed there. So those were the sorts of things you slowly just kind of do stuff, and it just grows on you, like biofouling.
Thank you very much.
Yeah, sure.